circuits for communication.
Thank you. It's a pleasure to be here. I look forward to the meeting every year. Where's the advancer for the slides? Oh, okay, great, thank you. In our group, we're basically hardware developers. We're building things in silicon platforms. And the title of the talk today is basically sampling everything. And obviously, I'm not sampling everything. But we're trying to get our hands on sampling everything from 0 to 18 gigahertz, which to RF people is more than necessary. My group is made up of students from a broad range of research projects that cover not only RF and microwave design in silicon integrated circuit processes, but also students working in baseband signaling or the periphery of baseband signaling with microwave design, students working on pre-distortion at millimeter wave frequencies, and in newer topics, we're moving into the idea of using silicon photonics or using optics integrated into native CMOS processes to do new things. And I'm going to talk a little bit about that today in conjunction with some high-speed sampling, the work of one of my graduating students, Tim Gathman, who is here today. This is basically just to showcase in 20 minutes some of the very interesting things we've found at trying to combine microwave, baseband, and silicon processing, silicon photonic processing all in one chip. So, where we're going with this, why would we want 18 gigahertz receivers is, well, there's a lot of spectrum sensing and cognitive systems that would like to take advantage of frequency spectrum that is basically unused above 10 gigahertz, 12 gigahertz, except for military applications. And so the kind of canonical software-defined radio might be a tunable filter, a variable gain RF amplifier, and then some sampling system at the back end, which might have more than 8 bits of resolution. But at this point, this was where our target was, is to stick towards 8 bits of resolution with a specified SFDR. Now, there have been some industrial efforts to try to build high-speed samplers in CMOS, and the state of the art right now is a Fujitsu 8-bit ADC, which at an input frequency of 17 gigahertz has an effective number of bits of 4.5. So this is a very complicated chip, well beyond one student's process. So we obviously need to go a different direction. It includes 1,024 SAR DACs and this is a picture of the layout of the chip, that are working together in a time-interleaved fashion to sample the high-speed signal. And at the core of that is the requirement of having low jitter between all of these different time-interleaved ADCs, or at least ways to control it. When we're talking about sampling very wideband signals or high bandwidth signals, where we end up looking on this Walden's wall of bandwidth versus SNDR is towards the very, very tippy top, as opposed to my colleague Ian Galton, who looks at very high resolution systems that are operating at much lower rates over on this side of the chart. We're specifically up against what's called the jitter limitation of the sampler. And specifically, when we look at getting out to 10 gigahertz or so, the kind of limitation we find is that a bandwidth of 10 gigahertz requires jitter that's under 51 femtoseconds. And if we try to go to even higher bandwidths, that jitter number comes down substantially. So we're at a point where we need to come up with ways to mitigate that aperture jitter and build systems that can take advantage of the lower jitter. And one of the ways that we can do that is to move away from electronics. And in some circles, that's heresy, but in our world, we'd like to think about how optical sampling can help an RF system, how optical oscillators can improve the performance of our system. And recently, a lot of work's been developed for mode lock lasers and for other types of optical sources that show that we can get down to attosecond timing jitter. And if we have that on chip, that's something that we can leverage to build a much higher resolution and much faster sampling system. Additionally, Some of the other innovations that are starting to appear is that we can build very, very low jitter sampling gates in optical systems, much lower jitter than what would be equivalent in an electrical integrated circuit. So we want to take advantage of three trends. The first is that the optical system can allow us to do a high fidelity copying of an RF signal onto multiple wavelengths, and that those multiple wavelengths would let us do some type of time interleaving. That the optical sampling will be much lower jitter and then allow us to do higher fidelity sampling. And then the third is that somehow we can take all these optics and put it into a chip that somebody can buy without ever worrying about the fact that there's photonics involved. And one of our collaborators, Professor Stoyan Radic, has been working with us to develop this type of system shown here. I'm going to step you through it because I think conceptually it's easy to get the gist of what's happening, and then we'll delve into the details of what we're trying to do with the circuits and why it's unique and important. The idea here is that we can take an RF signal in the electrical domain and essentially modulate that onto light through some Mach-Zehnder modulator. And once we've modulated it, that RF signal is now superimposed on a single wavelength. And then the magic is that in a single fiber, we can copy that RF modulated signal onto a bunch of different wavelengths with very, very high accuracy. So the RF signal will show up on red, green, blue, all the different wavelengths we have in our system, and still preserve more than 8 bits of resolution for the signal. We can then bring a sampling signal into our fiber and then sample all of these signals at once with a single sampling, single sampling clock. And so we preserve very, very high fidelity samples on the different wavelengths at the output of this zero jitter parametric sampler. And each of these colors can then be dispersed into one of n different channels in our receiver. So red might be filtered into the top channel, blue would be filtered into the bottom channel. And so what we would be getting is extremely narrow Gaussian pulses of light that represent RF signals that are time interleaved, but in this case, wavelength interleaved. So what we need to do is now build a very high resolution receiver that can capture these Gaussian pulses of light and integrate them in a circuit front end that can provide that signal to ADC, conventional ADC. So each of these channels does not need to work at that full 18 gigahertz. It's working at a much lower rate. So we would specifically maybe use 10 channels here to sample each channel at 2 gigasamples per second to build a higher aggregate rate of 20 gigasamples per second. But the problem is that getting these optical signals from the fiber into our circuit with high linearity is extremely challenging. These optical signals can have a very high peak power variation since they're sampling the RF waveform. And when we hit them with into a photodiode is essentially a reverse bias diode. It's a nonlinear circuit in and of itself. And as the power hits that photodiode, we get these non-ideal photocurrents out of the photodiode. There may be some ringing, and there can be some charge that's stored in tails after the primary peak of the Gaussian pulse. And so we need to use an integrating front end because we need to capture the total energy of that photocurrent. We want to capture all of that current. We don't just want to sample the peak of the pulse. And in fact, sampling the peak of the pulse is a big problem because we then have that same issue of needing high accuracy on our sampling clock to make sure we're getting exactly at the pulse of the signal, the peak of the signal. So we came up with an integrate and sample receiver shown here, which basically preserves the bandwidth requirement while providing at least 8 bits of linearity. This Gaussian pulse of energy is then received in the photodetector, which generates a current that goes to a GMC filter, which is providing our integration of that optical energy. We then use a master-slave track and hold to sample that signal and buffer it to provide it to an off-chip ADC. Since we don't want to build ADCs in our group, we're relying on the state-of-the-art national semiconductor ADCs, which operate at about 1.8 gigasamples per second and have a resolution of 8 to 9 bits. So we'd like our circuit to be much higher resolution or more linear than the ADC itself. Tim did a magnificent job on this chip. The chip is shown here, and it's packaged on a board with 2 channels. You can see the first channel coming in at the top being bonded into the silicon IC. This is, in fact, a silicon germanium IC. And then the output coming off at the top here, where it can be connected to an ADC. So each of these 2-channel receivers can consume 890 milliwatts. It's rather high power. But the idea is that it's at least going to show a roadmap towards integrating everything onto a single chip. Frequency domain measurements showed that as we got up to a bandwidth of our signal of 1 gigahertz, the E-knob dropped from just over 8 to about 7 bits at 2 gigasamples per second sampling rate. But this was all based on electrical testing. We then needed to go back to our collaborators' lab, take our circuit, and put it into their optical test setup. And so when we did this, basically we found that the original 2 gigasamples per second pulses here could be sampled with an RF waveform, basically a sinusoid in this case. And when we received these photocurrent pulses, our circuit, the integrate and sample circuit and the ADC showed up with the following spectrum. Now you'll see there's some distortion here, but it turns out that this distortion is all limited to our original Mach-Zehnder modulator, which was out of our control, and remains an open problem. But we could compensate for that modulator distortion, and we found that we had an E-knob of 7.5 bits on each of our 2 gigasample per second channels. That allowed us to do 20 gigasamples per second at nearly 7.5 bits. All right. So this was very, very promising, in particular with relationship to our Fujitsu ADC example, where at an input frequency of 17 gigahertz, the E-knob is only 4.5 bits. Okay? But nonetheless, it's a tabletop demonstration. Tim's also been working with them to show how a photonic sampler could go far beyond 20 gigahertz input bandwidth by using these laser pulses and then a differential modulator. The differential modulator can deliver differential pulses to the input of our receiver. And since the receiver would like to see that differential signal from the standpoint of linearity, we have a more relaxed constraint on the overall circuit performance. So the differential sampling circuit can now see both of these photocurrents as opposed to a single-ended photocurrent, which is then provided through the sample and hold to the ADC. And they've actually taken this and sampled not only at the Nyquist zone of 202 megahertz, but up to 10, 20, 30, 40, and 50 gigahertz. So input signals at each of those different Nyquist zones have been subsampled down to our original Nyquist zone. And the SNR, as you can see here, starts at 48 for the Nyquist zone, and then at the higher frequencies falls off, but starts to flatten out around 38 dB. So this shows some very interesting things. When we look at a signal at 49.8 gigahertz here, and that's sampled, only at 2 gigasamples per second, it's aliased down to 200 megahertz. And the E-knob that we're seeing, once we estimate that modulator distortion, is 5.7 bits. So this blows the electronic, anything that could be done with an electronic IC out of the water. Hopefully I've convinced you that the optical copy can be done, the optical sampling can be done, but the next step is what we're specifically interested in, which is how to take it all and put it in a chip. And so some of our other research is involved in looking at taking photonic devices and putting them into native silicon processes that don't require additional processing. And this has been something that's been pioneered through silicon on insulator IC processes, particularly Freescale Semiconductor, has developed a 130 nanometer SOI process, which has been gaining a lot of attention for its ability to support optical light propagation in a waveguide formed between the barium oxide layer and the silicon dioxide of the back end of the line. So this optical waveguide shown here will allow light to propagate through it, but the velocity of the light can be changed by controlling the applied voltage across that waveguide. And so this has allowed some optical scientists to build photonic microring resonators. These microring resonators basically have a linear waveguide which will take the optical light and couple it into this ring. And when it's coupled into that ring, it's basically stored like in a cavity. The Q of this circuit is the Q of this photonic device is quite high. It can be greater than 10,000, even greater, close to 100,000. So it's extremely high Q relative to what we see at RF with RF devices. But the neat thing is that the resonance can be controlled by that reverse bias diode. So again, by applying a voltage across this waveguide, we change the center frequency of the resonator. And so we have a very simple way to control where our resonance occurs, which can be low power if our voltage swing is constrained. And our current work shows that it's about 1 volt. So it's extremely compatible with current CMOS. But how about high speed? Can this operate as a high-speed circuit? And what we've done is taken an entire optical transceiver and put it on a single chip. That includes channel coding, a modulator, and in this case, because our optical device is really just a reverse bias diode, we don't need complicated drive circuits. We're just using inverters. Just very low power inverters to drive the cathode and the anode of this reverse bias diode and modulate the light. So we've built the entire transmitter at 25 gigabits per second. We couple the light in and off chip so that we can look at it, but then we can couple it back in, and we've built a 20 gigahertz bandwidth receiver to then capture the signal. So this requires two devices, the ring modulator and then a photodiode, which is, again, also part of the Freescale process and has a bandwidth that's about 20 gigahertz, depending on how it's engineered. This is a picture of the chip. This got the transmitter circuit over here on the left, and you can see this little tiny cutout where our photonic ring modulator is. The ring modulator is blown up in this inset image. It basically is about 20 microns across. It's a very, very small device. The connection to the anode and the cathode are shown on those the two metal layers coming in on the top. And basically, the optical waveguide brings the light in here through a waveguide that can't be seen. So I've drawn it in black, up and around past that ring resonator, and then off chip where we can observe it. And then our RX comes back on chip to the receiver over here. One of the neat things about working with optics and silicon chips that's different than RF chips is you can actually see your signals. And in particular, this is an infrared image of this chip operating. When it's tuned appropriately, the light is absorbed in that ring resonator. And so you'll see as it tunes, the light will be coming in here on the right. It's kind of leaking in the waveguide a little bit, but then there's a very bright spot that is co-located where this ring modulator is. And then the waveguide on the output is much lower intensity because you've absorbed the light. And that's exactly what we're going to do, but we're going to do it at 25 gigabits per second. We're going to do it at 40 picoseconds, turning this thing on and off to absorb the light into that ring and then allow it to pass. This is a picture of a measured transmission spectrum, a measured transmission response of the ring here when we apply a 0 and a 1 to the voltage, cathode and anode voltage. And you can see we can shift that voltage, we can shift that wavelength from about 1561.6 nanometers to just slightly above 1561.7 nanometers. And so the difference between 0 and 1 here gives us about 8 dB extinction ratio, the ability to turn off the resonator and then allow light to propagate through it. Here's our results. Amazingly, We've shown that we can do this at 20 gigabits per second. We can even push it to 25 or even 27 gigabits per second with clean open eyes supporting 10 to the minus 12 bit error rate at 25 gigabits per second. So the Freescale process shows a lot of promise to do high bandwidth, microwave types of bandwidth on, with photonic devices, modulating photonic devices. So we'd like to move forward looking at putting all of these things together, sampling signals in the microwave regime with not just electronic circuits, but also using photonic techniques. We've demonstrated that sampling at 50 gigahertz can be done with just under 6 bits of SNR. We've also demonstrated that we can build these photonic links, we can modulate these photonic devices at very high data rates. And so we have a platform now where we can do heterogeneous integration of electronic and photonic circuits together that we believe will ultimately support higher speed RF systems. So in conclusion, I should say some of this work has been funded through the CWC, but I also get some support from DARPA, as well as ONR, and support through Panasonic and Nokia Siemens, as well as the NSF through the Career Grant. So, can I take any questions? Yes? So, this resonator here has a Q of about 16,000. The Q is determined by the 3 dB line width over the wavelength. And so if you go through that calculation, you have about, let's say 0.1 over 15,000, 1,500. So that's about 15,000. Okay? Now, this ring, I should apologize. I did this in collaboration with some optical scientists at Oracle, and they engineered this ring. And so specifically, you can change the geometries to allow you to get higher Q but lower bandwidth. And we were after a ring that would have a relatively low Q of only 16,000 so that we could modulate it at 25 gigabits per second. You can build rings that have even higher Qs than this. Does that make sense where the Q comes from? So if you just take 1561 nanometers, you divide it by 0.1 nanometers, that gives you about 15,000 for a Q. Yes? That is where we need to go. So the Fujitsu ADC consumes about 8 watts, okay? This circuit, for instance, consumes 40 milliwatts, but I'm not counting the laser power, okay? So if you want a fair apples to comparison, you should be wrapping in all of the laser power, wall plug efficient laser power, and all these different wavelengths. And so there's a lot of challenges with that. And I think if you're looking at doing the silicon photonics work, the kind of work we're not looking at right now is how you build lasers on chips and multi-wavelength lasers on chips. And that type of work will be crucial to making low-power photonic sampling systems in silicon and being able to do the type of apples-to-apples comparison you're suggesting. But the electronic samplers are not low power. I mean, 8 watts is not going into a cell phone, right? So hopefully down the road, we will be able to show that these things can be done at under a watt, very low powers. Well, people in the optical community would like to do this 100 gigabit Ethernet, so doing multiple lanes at 25 gigabits per second. And that's why we were targeting that application here. And then if you wanted to do, increase your data rate, your capacity, you might want to do things like QAM over an optical fiber, and then you'd need the linearity that we talked about in the previous part of the discussion. In the RF world, I think that there's some radar applications that would love to have extremely high resolution, high bandwidth receivers. Yes, Renee. This is a commercially available free-scale process. This is, there are several companies that use this as a startup business model. They use this free-scale process. So it's available, it doesn't require any tweaking, and it's relatively, I think, cost-effective when compared to other types of bulk CMOS processes, like 90 nanometer CMOS. I think it's very comparably priced. I think it could be very cheap, yeah. Yeah, so that's where we come from. We're not interested in fancy processes. We're interested in using very traditional, conventional processes that can be commercialized in the long run. And so we'd like our techniques to be compatible with those types of IC processes rather than doing something that's extremely exotic and will never see the light of day other than in some government lab. All right, thank you.